Hello, 4C Group. Welcome to the first lesson for the electrochemistry unit. The goal of this lesson video is just to introduce you to the principle of oxidation reduction, as it's commonly called redox, and you'll encounter some um, types of reactions in this lesson which are familiar to us. We've looked previously at the activity series, which is somewhat related to this concept of oxidation reduction. We've done questions in the past where we've had to balance reaction equations, and we may have even balanced them and identified the type of reaction equations. Looking at these now, which of those would involve oxidation reduction? Well, we can't say because we haven't defined the terms, but what we can say is that surprisingly many of them would actually involve these complementary processes of oxidation reduction. So let's explore this a little bit more and try and understand what we're talking about here. So oxidation reduction can be demonstrated very easily in chemical reactions. Common reactions that involve metals and metal solutions are really good candidates for oxidation reductions. Let's look at why.
When a piece of copper metal is placed in a solution containing silver ions, solid silver crystallizes on the copper. While the silver crystals grow, copper ions are also released into solution, giving the solution a blue color.
So what's worth observing in this reaction? Well, we start out with elemental copper, and although it's not immediately obvious, there's no solution there. When the solution is poured in, it's a clear solution. And as we see the reaction progress, we notice that gradually the color of the solution is changing from clear to blue, and we see that the element copper is gradually reacting, and a new metal solid, the element silver, is forming on its surface. And so this is a complementary process where one element becomes an ionic compound and another ionic compound converts into elemental form. This, of course, is a single displacement reaction. And that's why the connection in this lesson with the activity series, which is relevant in that elements that are higher on the activity series are more likely to displace elements from compounds lower in the activity series. The direct application would be predicting whether or not single displacement reactions take place involving two metal elements. So in that reaction, as we saw, copper slightly higher than silver in the activity series does displace the silver from silver nitrate, and the element silver is kicked out as a result, and solid silver is formed, whereas copper nitrate would be the preferred product when those two elements are in the presence of each other. So here, this particular reaction involves an element copper and a new element silver. And in each case, we have neutral atoms, and we have charged ions. In a case where charges are involved, and in particular where charges are changing from one element to another, this is a classic example of a redox reaction. It's very easy to spot, and it's the simplest type to spot, which is why we're starting our lesson with this type of reaction. So if we look at another type of reaction, zinc and copper sulfate, copper 2 sulfate, here this too would be an oxidation reduction reaction. Let's understand what the two processes are that are going on. So to help us, we're going to take that reaction equation, which is already balanced, and the forms are all correct. We have solid, aqueous, solid products, and we're going to write the aqueous reactant and products as ionic particles. So this is what's called a total ionic equation. Anything that is in an ionic state is written with its charge shown. So these are copper 2 plus and sulfate ions present on the left side, and we have zinc 2 plus ions and sulfate ions on the right side. You'll notice that the sulfate ion really doesn't react at all in this particular combination. It's there to provide a source of copper 2 plus as it's bonded with the copper 2 plus. And in the product as soluble zinc sulfate, it really is still present as sulfate ions. So what do we have that's changed? Well, we do have zinc, which has been converted from an atomic neutral particle into an ionic charged particle, and we have the reverse of that taking place with the copper. So to isolate really what's happening with the chemistry of this reaction is, let's get rid of the spectator ions. This is called a spectator ion. We've seen that before. It's just spectating, it's not participating. The net ionic equation shows what has changed. In this case, zinc has been oxidized from neutral atoms to charged ions, and copper has been reduced from 2 plus ions to neutral atoms. The charge on both reactants is changing. A neutral zinc atom loses 2 electrons to form an ion. It would lose 2 electrons, obviously, to obtain a 2 plus charge. The copper 2 plus ions must have conversely gained 2 electrons to become a neutral atom. So we can see how these processes are complementary. One is called oxidation, and in this case, the oxidation is the loss of electrons from an atom to another particle. It also involves an increase in the charge of the element, whatever the particle is. So electron transfer has this process combined, paired up with the opposite process, which is the reduction. This is a gain of electrons, and it's also a decrease in the charge of the particle. In this case, 2 plus is a bigger number than 0. So there's a reduction or a decrease in the charge. So that's called reduction. So redox reaction always involves these two paired up. They can't happen in isolation. Electrons would only be transferred if there was a particle to accept them. The oxidation of one element is a loss of electrons. The reduction of one element is a gain of electrons. And these two unique but related processes are what we refer to as redox or oxidation reduction. There's some ways that we can remember the two types of reactions. Down at the bottom here, you'll see some mnemonics, which are little word tools that we can use to memorize some scientific ideas. So Leo says Gur is one and oil rig is another. So you can figure out how those two mnemonics work. So we've introduced oxidation reduction. When we proceed a little further with this topic, we will eventually want to identify the oxidizing agent and the reducing agent. For now, we'll just observe that the oxidized reactant undergoes a charge increase, becomes more positive, and the reduced reactant undergoes a charge decrease, becomes more negative. And we could rightly say that zinc reduces copper 2 plus, and copper 2 plus oxidizes the zinc. The term oxidation you may have previously thought of involving oxygen, and that's not necessarily the case. When oxygen reacts with something in a combustion reaction, oxidation also takes place in the sense of a loss of electrons or in the sense of an increase in the charge on the particle. But strictly speaking, for redox, oxidation involves an increase in charge / loss of electrons. You're filling in this handout as you're going along. Should now be complete. Let's look at some examples here. So all these reactions here are oxidation reduction reactions. We're going to identify the oxidized reactant and the reduced reactant in each reaction. It would be helpful to have a little bit of space in between to write ionic equations. The net ionic equation is most important because it isolates those particles which are being converted into ions or which are being converted into neutral atoms. So here we already have the net ionic equation shown for the conversion of calcium to 2 plus and tin 2 plus to tin atoms. So here we would say that the oxidized reactant is the one that is increasing in its charge. So this is the being oxidized And we can see here that to go from calcium to calcium 2 plus, this is a loss of 2 electrons. You have to take away 2 electrons from calcium atom in order to get a calcium ion. So loss of electrons must be the reactant which is being oxidized. Likewise, we have tin, which already had a charge, and it is the reactant which is being reduced. And in this case, we can see that it's being reduced because to go from charged particle with a positive charge to no charge, it had to have gained 2 electrons. So those 2 electrons which were missing from its valence orbit have now been restored, and that tin would now be, we could say, precipitating out, which would be accurate, but it's also being converted chemically into the element, the metal element from the metal ion. So when you go through here, what I would recommend you do is to identify the charge on all the particles. So anything which is an element has a charge of 0. Anything which is an ionic compound has a charge equal to its valence. So copper has 2 plus paired up with sulfate 2 negative. We can go along here and identify all the charges, and then when we look at the element on the left side and the same element on the right side, we can identify here what's happening. So to go from 0 to 2 plus, this is an increase in the charge, so this must be oxidation. There would have to be a loss of 2 electrons. To go from copper 2 plus to copper elemental, we would have to have a gain of 2 electrons. So that is obviously gain of electrons slash a lowering of the charge is reduction. So we would be able to identify magnesium as the substance which is being oxidized, and copper 2 which is being reduced. Notice the sulfate undergoes no change. Sulfate exists as sulfate as a reactant, exists as sulfate as a product. There's been no change to the charge of the sulfate. So it is not being oxidized or reduced, but it happens to be participating, or at least spectating, I should say, in an oxidation reduction reaction. Oxidation reduction reactions are very common. They're involved in the function of batteries, and a lot of chemical reactions are carried out to actually generate electrical current, and in some cases electrical current is used to make chemical reactions work. So it's very important we understand, to complete our appreciation of chemical reactions, that transfer of electrons also involves a change in the oxidation state of elements, and that's what's really key here. So as you go through the remainder of this, I would just encourage you to try to identify as much as possible the charges. Try also to, if you can, get a little bit more practice here, write the net ionic equation, and you can easily spot the spectator ions. You can see in the next reaction the nitrate is spectator because it's present on both sides and there's been no change to it. Chloride is spectating in part D. The last 4 reactions are not involving binary compounds. They, in one case, is a synthesis reaction for E and F, as well as G and H. So we don't have a spectator ion in this case. We have oxidation reduction, but what we could do in C and D is at least write the net ionic equation. So we can identify that there's 2 silver ions here, and each bearing a charge of +1. Those are aqueous. I won't show the nitrate. I've got zinc solid, and those are reacting to form 2 silver atoms and a zinc 2+ ion. So you notice with oxidation reduction reactions, when you write the net ionic equation, you should have mass conserved. The number of particles of each element should be identical, and you should have also charge conserved. That's really key that you identify that as well. So when charge is conserved, you should see the same amount of charge on both sides. Count the charged particles on the left side. There are 2 of them. They each have a charge of +1, so total charge is +2. And on the right side, we also have a total charge of +2. That's how you really know you've written your net ionic equation correctly. And again here, with this one, we have zinc being oxidized, and we have silver 1 plus being reduced. Okay, so you're going to complete that before you come in tomorrow. When we do come in, we'll look at some section questions here. We're also going to go back and review the activity series a little bit just through the reading of the section in the Chapter 5 textbook for the 4C manual that's relating to activity series, and just a couple of questions to review how that applies. So at this point, this concludes the video lesson, and we'll see you tomorrow.